right? Even if it's not going in a circle, it's a semicircle. It's a piece of a circular path. It still has an angular velocity. And so while it is rotating in the direction it's about to rotate, it'll be pointing out of the board, positive. But right now it's 0, because it's not moving. Okay, so what direction is angular acceleration pointing? Positive out of the board. Because that's where it's about to send the angular velocity vector. Yeah. Now, actually, this doesn't have a lot to do with circular motion. It's more relativity that people sometimes. Have you guys seen the original Superman movie? It's hokey. And hokey is like, man.
I think part of it's like you can. It was made in like the so you can tell all the bad special effects.
Right, but then there were groundbreaking special effects. Like the original trailer for the movie is like, see Superman actually fly.
Yeah,
it's funny. Hokey means, I don't know. I don't know how to define that for you. It's like
silly, not believable.
Yeah, silly, not believable. That's good. But in the movie, Lois Lane kind of dies at one part, and it's really slow. Well, I said, you'll understand why I said kind of in a minute. It's a slow, drawn-out death, and it's kind of weird. And she gets covered by a landslide. And Superman gets really angry, and he's like, no! And he flies up into space, and he starts flying around the world. And this is what it looks like. This is the scene from the movie. He's like, I mean, this is not. I added that, but the background picture is. And he's like flying around the world super fast, and like you see the Earth like stop rotating and start rotating the other way. And then you watch the like really drawn out scene you've been watching for the last 20 minutes backwards, and Lois Lane's like okay again, sitting in the car like, no! And he flies down, he saves her. And people were like, well, how is that possible? Like, did he like impart rotational motion to the Earth? Like, did he exert angular acceleration on it and like make it spin the other way? And why does that make time go backwards? And I mean, there's no good physics at all, so we can just like leave it behind. But if you really want to try and apply physics to this situation, I would say that it's more of this equation. And we've talked about that equation before. Where is that from? Time dilation. What is time dilation, Andrew?
Where when you start moving, because the speed of light has to be, the speed of light is a law, so time will bend in order to preserve the speed of light.
Yeah, you're absolutely right. It just sounds crazy every time you say it. That's absolutely right. The speed of light's a law, and so time bends to meet the speed of light. So it's more like Superman, and this is bad physics here, so don't you dare quote me on this. He went faster than the speed of light, therefore time went backwards. That's a bad therefore. And then saved Lois Lane's life. So, not a lot to do with circular motion, but a little bit. Yes, Mr. Cameron?
Where does the denominator come from?
This Pythagorean theorem. Okay, sorry, PowerPoint kind of freaked out on me and cut off the bottom of this, and I can't fix it. The whole image is locked. And so I've got to go and I've got to go redo this slide because I made it this morning. But here we go. It's also a famous Spanish literary figure.
I know that's
A windmill is spinning vigorously on top of a mountaintop when sudden wind dies. The angular speed of the windmill's blades decreases according to the equation law. Find the equations for the blade's angular acceleration and angular position, and then graph. This is what's not visible. The equations, all three of them: angular acceleration, angular velocity, and angular position. I intentionally did not tell you the initial conditions, but that does not mean there are not any initial conditions. You need to be able to figure that out. Possible.
Oh,
initial condition that you do always assume is that at time equals 0, theta not equals 0. That's something you always should assume. That at time equals 0, theta not equals 0.
Top here. Oh, well, I mean, yeah, you could plug it in. 9/2? Yes, but it shouldn't be. Do you know how much time?
And he said that assume that.
Okay, so when you take the antiderivative, you don't get that theta naught term on there. I put that on there, because that's my plus c. We always assume that at time equals 0, or at theta equals 0, so that we can measure from when we start the clock. It just makes sense. And so, if you put in 0 and 0, you find out that the plus c term is 9ln2. Otherwise, your graph looks crazy. Doesn't make any sense. Yeah, keep going. Alpha of t is equal to negative 9 all over 2t plus 2 squared. Easy calculus, right? Hey, are you getting more comfortable with this yet?
Yes.
Good.
It's just the weird Greek.
It's just the weird Greek is weird. I don't
Wait.
like Greek.
How'd you get the first one?
How did I get first one?
Yeah,
I took the antiderivative.
Oh.
I did something.
Somehow we'll
Remember that the integral of 1 over x dx is equal to ln of x?
Yes. I got 9 that one.
Where did I get this from?
Yeah.
Because there's a plus c term.
Oh.
This is always true.
I have a question. How do you solve for C?
At t equals 0, theta not equals 0. So replace theta if t was 0. Replace t with 0. 0 equals 9 ln of t plus c. Got it? Okay. I think I'd probably be a lot more patient with the calculus questions if y'all weren't in calculus right now. So it was like, it's okay, you saw it last year, but it's like, you saw it like last block.
Actually, it's next block.
That's actually true because it was last block.
Depends on who you are. Okay, if you graph these, theta of t should look something like this, I think. Right?
Yeah.
Approaching some kind of asymptote. What's my asymptote?
9.
As time approaches infinity, what's the element of infinity?
It's 0.
It's 0, I think.
Yeah.
I think the element of infinity is 0, am I right?
Wait, I think it's like
It's not infinity. That's what we learned in calculus.
Yeah, element of infinity is infinity?
E to the infinity is infinity.
It didn't let me do the element of 9999 E 9999.
It's infinity, it's infinity.
Yeah, I broke my calculator trying to do it. Why is it? It said error overflow. Okay, in that case, I guess there's not an asymptote. My bad. I made this problem up and didn't think too much of functions, so it was kind of last minute. Omega of t. We are going to reach a constant speed, right? So even though we'll keep on rotating, it just will be very slow after a while. What's it going to do? It's going to approach 0? And what's my y-axis? What are our constant axis?
9/2.
9/2. I do know that one approaches 0. Cool. And alpha of t. What does it look like? Positive or negative 9/4?
Negative.
Because it's slowing it down. And it does this. Cool. Okay, we're going to do this conceptual practice on Monday. We're going to learn some new stuff now. Because I think it's your best interest to just kind of like get these concepts under your belt pretty quick so that you have time to absorb them. The test, for those of you that care, this is today. Oh, not today, sorry. This is today. That was Wednesday. And so, not next week, but the week after, that Thursday, which is the day before Good Friday, we're going to have a quiz over all this stuff. I might move it to Wednesday.
Yeah.
Okay, so there'll be a quiz that Thursday. Then, unfortunately, spring break's a week later this year.
Oh darn.
Which,
A week later?
yeah, which is a bummer, because normally what I do is I give you spring break, and then the week after spring break, we have the rotational motion exam. But you don't get spring break this time. So you have kind of one less week to absorb it, which is still a lot of time, right? You get 3 weeks to learn all this information.
How many chapters is this in the book?
1. Maybe 2. I think it's 2 chapters. Might be 2 chapters. Maybe 3. April 5th. April 5th is going to be your rotational motion exam. Okay? Now, I would be willing to talk about putting the exam maybe on this Monday. Just to give you a week, but I feel like you wouldn't study. And I'm not going to be here that Monday. So,
No, give it to us before spring break.
I think I should get you before spring break.
Yeah.
the actual final?
Yeah.
So, it says the test is on Friday.
I'll fix it. I need the website does that. Okay, I want you to answer this question with the people around you. Go ahead, read it.
Where do I find them? Because I don't think I'm
Yeah, I know. Hey guys, everybody, I think you should read all the stuff on rotational motion this weekend. I think you should commit to it, because that way when I talk about it in class, you'll be like, I got it. Even if you read the book and you're like, wow, I don't know what this is saying at all. That way the book is the first time you see it, which will be kind of confusing, and that way when I explain it, it won't be as confusing. So if I were you, I would commit to reading everything this weekend on rotational motion. Just knock it out. You don't have a lot of other work for me, so you should really commit to that. It will make this unit and the upcoming test a lot less stressful. Focus on answering this question now.
Specifically on the acceleration.
Sure.
Why is the magnitude of acceleration not being
Because it's kind of like it's the speed is slowing down, and the acceleration is kind of drag as a function of speed. It's kind of like a drag force problem that we solved earlier in the year. You know how like we have blocks that like slide in the air friction and they're slowing down? Same basic idea.
Yeah. I think where I wonder
Yes, we know this one. Experiences we have had as human beings. That experience.
Not always.
When you roll a shape that looks like that, now it's like, what happens? Come on, everyone's done that.
Okay, we're going to test it, because we're scientists. Science. Okay, so, Andrew, raise your hand a little bit. Well, that's a lot, but a little bit more. Okay, there, perfect. Okay, so we're just kind of, I'm just going to roll these back and forth, and I want you to kind of make some observations. It's crooked right now, and it's going to, straighten itself out. Clever. Notice how, when it starts to roll crooked, it self-corrects. Whoa. What the? Crazy physics. Isn't that wild? Alright, now watch this. When this one starts to roll crooked, it's like, woohoo, crooked! And it launches right off. And go cup of science, go. Man, I can't even get right. This is the challenge. I've got to get it to roll to Andrew's hands. Game time.
Is Andrew holding it straight?
Yes, because he's on my team. He's trying to make it happen too. Go, go. I can't even get it to the 50 centimeter mark.
Maybe that
Massive
should be
fail.
your first goal.
Go,
Start small.
and ready, set. I rolled it to the 10 centimeter mark. That's my first goal. Alright, so this guy is out of control. It starts to turn and it turns really fast. This guy self-corrects.
Can you do this? I'll cut one again. So what do you mean it's Oh.
Watch, I'm going to put it crooked. It's going to look very crooked, right?
Yeah.
Roll. Yes. Whoops. Alright, crooked and. Oh. Physics works. Okay, I want you now, with that observation, to talk to the people around you and try and figure out why that happens.
I know why.
Main ends are small, but I like not necessarily the ends are what's touching
Yeah, this is yeah, that was even though it's a lot of I used to think it before he did that. I think like force and have a bad but I don't know how to do it. Yes. To me, I think that has maybe it has greater.
Okay, Chris, go ahead.
Can I explain it on the board?
Yeah, go ahead. Take the board. And just because I didn't talk about it while Chris is getting set up, number one has neutral stability. And so it's not going to have a tendency to do anything. It's stable over short distances. Go ahead, Chris.
So, we have our track. Let's say, look at number 2, right? Once it becomes crooked on the track, then you're going to end up with a much larger diameter here on this side that's touching the track than here on this side. So because you have a larger diameter of or a larger circumference of the cup touching, then it's going to travel a greater distance per rotation on this side. So it's going to cause the cup to turn and fall off the track, because this side is moving slower than that side. However, if you have this one where the cups are facing inward, then if it becomes turned, then you have let's say it's turned this way, then you have a smaller diameter on this side and a much larger one on this side, which causes it to turn that way and auto-correct itself. Because it's the side that has the larger circumference is going to travel faster until they're both traveling at the same speed, so it's going to wobble until it goes straight.
Yep, absolutely right. On the same note, thanks, Chris. That was a good explanation. I'm going to add to that explanation with this in. I got some tomato paste with roasted garlic. Expired in March 2007. Let's see, March 30th, 2007. I think I was in the hospital then, in Spain. I'll tell you that story later. Okay. I was in Spain for sure. I think I was in the hospital. You know what? I think I might have been out of the hospital by then.
As in, like, in treatment or working in the hospital?
I was a patient. I'll tell you later. Alright, now watch. If I roll the ancient tomato paste, it rolls in a straight line. Didn't expect that one. If I roll a cup,
I did not expect that.
it rolls in a circle. Who wants to explain what's going on? Go ahead, Austin.
I think it's because when you roll the paste, each side has an even circumference, or the circumferences are equal, so they're both spinning the same amount per revolution. Whereas with the cup, you have one larger circumference and then one smaller circumference at the top. So per revolution, the smaller circumference is traveling a less distance than the larger circumference. So the outside is going to spin. It's going to appear as if it will spin more distance in one revolution.
Absolutely. It's a great explanation. How about this? I'm going to add on to that with some math terms, or physics terms. Every spot on this cup has the same angular velocity. Same angular velocity, different radiuses, right? Which means different tangential velocities, which means one's going to be covering more ground faster. It's moving faster. And so it moves in a circle. Here, same omega, same speed. Chris?
So, because the outside is also moving faster, then that means because the outside and the inside, it'll roll in a circle because the outside is moving at a faster speed, and therefore it is further from the center of the circle that the cup makes when it rolls.
Aha, yes.
So that's why it rolls in a circle.
Cool. Okay, let's learn some new stuff. Rotational motion. Wait, I missed my animation. got some serious hula hoop action. We got some 80s rock. You spin me right round like a record, baby, right round. What is this?
A flower.
Oh,
the helicopter.
They go in circles. It's a maple leaf. Do you guys know what this is?
Record player.
Oh, it's a
It is what the cavemen use. Yes, that makes me caveman. I must be related to the Neanderthals. We'll do this later, but just kind of as a note, the idea of this one being more stable, I don't think I mentioned this, but you should know that the center of mass for this cup is in the same location as the center of mass for this cup. Center of mass didn't have to do with the stability of the cups. Okay,
I mentioned this earlier.
trains use this design to stay on the tracks. Kind of neat. Let's do this later. I want to talk about this. What is inertia? Change
Anything.
motion. Well, yeah, but change in motion is how we talk about it. You know, we did talk about thermal inertia, but inertia by itself is just resistance to a change in motion. What do you think, guys? Does inertia affect an object's willingness to start or stop spinning?
Yes.
Yeah? Give me an example that proves your guess. Awesome.
It's really easy to spin, say, a quarter. It's very hard to spin, say, Stonehenge.
It would be hard to spin Stonehenge. Kevin?
That thing where like the guy puts like the bicycle wheel on like the rod and tries to turn it, doesn't like let him, something like that. I don't really know how to describe it, but I've seen that. Like someone spins the bicycle.
That's
tries to
something
turn it,
else.
It doesn't let you. Oh, it's not this.
That's not this.
Crap myself.
Joe?
We were in space, pretty gravity. It would spin forever. If we start spinning it, we never stop.
That's a good, that's great. If you're in space, free from any external torques, not external forces in this case, an object that starts spinning is just going to keep on spinning. It's got no reason to stop, unless an external torque acts on it. Now, if this rod had been made of the densest material known to man, it would be hard, not rod, wheel, it would be hard to start spinning it. And I wouldn't be too keen to stick my finger in here and make it stop spinning. But if it was made from like ABS plastic or something, it would be very easy to start it spinning. And it would be very easy to make it stop. Let's think of two wheels made of the same material, of the same mass. Same density, same mass. But they are manufactured differently, so they look different. And therefore have different, let's call this term rotational inertias. Willingness to start or stop spinning. Speed up, slow down, spinning. How might you distribute the mass differently on two wheels with the same amount of mass to make one have more rotational inertia and the other one have less rotational inertia?
You could, I'm not sure that would be which, but you could center one mass on the rim, on the outside of the tire, and then I'm not sure which one that would be, but then send one mass instead of.
So for one of them, we're going to put the mass near the axis of rotation, and one of them, we're going to put the mass really far from the axis of rotation. What do you guys think? Which one's going to be easier to spin? Which one's going to be harder to spin? Yeah, do you think farther from the axis is easier to spin?
No, it's harder.
You think it's harder to
Yeah.
spin?
Mhm.
Why?
Because for every degree that it rotates, the material on the outside has to move faster speed. Therefore, you're giving it more momentum, and so you have to apply a greater force to it.
It's a good perspective. I like that. Andrew?
It would be easier because you're exerting
What would be easier?
to spin it on the rim
Okay.
rather than in the center, because you're exerting an external torque on it, and torque is the force you're applying times the distance from the radius, so you'd get more torque if you were on the rim. So it's easier.
Well, why do I get more torque when there's more mass on the rim?
Well, no, it'd be harder if you put a lot of mass on the rim, because,
I thought you said it would be easier.
no, it's easier to spin from the rim, so you put more mass.
Oh yeah,
on
we're
the
not talking about where it's easier to spin from. We're just talking about making two objects, one that's easy to spin, one that's hard to spin. How about this? If I put all the mass on the axis of rotation, but then like extended a really thin frame so that I could still grab it at the same point that I would grab the other object to spin it. And then the other object, same shape, but all the mass is at the rim. The object with the mass on the rim is going to be a lot harder to spin than the object with the mass all concentrated at the center. You kind of get that idea, Austin?
If you had something, this is entirely theoretical because you can't do it, but if you had something that had no thickness, it wasn't a 3D object, it was just like a straight line, wouldn't it be impossible to spin because you can't exert the torque on it?
It'd be infinitely easy to spin. Oh, I see what you're saying.
Theoretical, I know we can't actually do that.
Well, subatomic particles have spin.
Theoretical subatomic particles.
No. I'm gonna have to think about that question. Okay, we'll do this on Monday. So, the rotational inertia is called the moment of an inertia. An object's moment of inertia is its rotational inertia. And what two factors affect moment of inertia? What do you say? What two factors? Mass.
Distance from radius.
And what we'll say actually is the distribution of mass about the axis of rotation. So, the mass of an object and the distribution of that mass about the axis of rotation are what affect rotational inertia. So why do tightrope walkers carry these huge poles as they brave terrifying heights? Think about it. Okay, sure, it is for balance, right? If you're walking on a fine line here, you're going to hold your arms out like this. Why does that give you more balance than walking like this? It does. Why does it give you more balance? Your center of mass is a point.
I mean, you still have the same center of mass with or without the pole, assuming you're holding it in halves.
Well,
it's distributed more over a wider.
When we did this question in our center of mass unit, remember we wanted big droopy poles. We wanted the poles that would droop down. Why? Lowers your center of mass, right? More stability. So we're not talking about drooping. We're just talking about this versus this. Patrick?
Because the pole like extends the radius, and so you could like tell if you don't make the pole move as much as at the ends, the angle doesn't change as much as if you're like closer. It wouldn't be as precise.
Okay. Yeah, if we distribute the mass away from the axis of rotation, where is this lady's axis of rotation? Not her center.
Her feet.
At her feet. Yep, if she falls, she's going to fall. If she falls, she's going to fall like this, right? I rotated about my feet. Or the other direction, right? So her feet are the axis of rotation. So when she puts her arm like this, she's distributing her mass outward. Why is this better than this? Because technically here I'm distributing my mass even further away from the axis of rotation. Oh, wind blows? Doing this does not magically turn into a sail. Inside, whatever. Like, well, why is this not as stable? Awesome.
Nah, that's not the right answer.
Yes?
Your center of mass is now higher.
Yeah, she just raised her center of mass. Higher center of mass is less stable. Right? So you want a low center of mass for stability. You want a well-distributed mass for stability. So this is kind of our thing here, right? This is stable too, but it's a high center of mass. And then this is less stable. You should try it. Walk in the halls today like this. See you guys. Have a good weekend. Walk in the halls like this. Feel your stability change. And then while you're at it, be like, all you guys only see my angular speed right now.
I'd like to point out that all of this must be avoided by simply not walking on tight ropes above New York City.
Alright, two shapes, same mass, different distribution of mass. Therefore, different what? They have same mass, same shape, different distribution of mass, therefore different
Rotational inertia.
rotational inertia, aka moment of inertia. Small moment of inertia, large moment of inertia. All that calculus we've been doing with center of mass is going to come back real strong. Oh, math. Okay, guys, that's all I got for today. You want to watch a minute of this video?
Can you tell us how you ended up in the hospital?
Oh yeah, I had appendicitis.
That's lame, man. I was expecting something cool, like I took part in a revolution and got shot.
I did. I did because the right years one time. And yeah.
And Harlan, you want